MH370, contact HMIN 120.9.
It's been 11 years since the disappearance of flight MH370, but one company is so sure they can find the wreckage, they put $70 million on the line.
It remains one of the most profound aviation mysteries of our time. A modern Boeing 777 Malaysia Airlines Flight 370 vanishing on a routine flight from Kuala Lumpur to Beijing over a decade ago. For years, the world watched as vast searches yielded nothing, leaving families in agonizing limbo. What happened to MH370 and the 239 souls aboard?
Good night, Malaysia 370.
The questions have echoed unanswered, but now whispers of breakthroughs born from cutting-edge science applied to unlikely clues suggest we might finally be on the verge of pinpointing its final resting place. Before the silence, before the mystery became an indelible scar, on modern aviation, March 8, 2014, began like any other day for the passengers and crew of MH370. The Boeing 777-200ER, a workhorse of long-haul travel with a solid safety record, lifted off from Kuala Lumpur International Airport shortly after midnight, local time, bound for Beijing. On board were 227 passengers, a mix of tourists, business travelers, families, artists, and engineers, along with 12 Malaysian crew members. The flight climbed smoothly to its cruising altitude of 35,000 feet over the South China Sea. The early stages were utterly unremarkable. Standard radio communications occurred between the cockpit and air traffic control. At 1:19 a.m., as the plane prepared to transition from Malaysian to Vietnamese airspace, one of the pilots, widely believed to be co-pilot Farik Hamid, uttered the now infamous chillingly routine phrase, "Good night, Malaysian 370. This was the last voice communication received from the aircraft. Everything appeared normal. The abrupt disappearance triggered immediate alarm. When MH370 failed to check in with Vietnamese air traffic control as expected and couldn't be raised via radio, the first tendrils of worry unfurled. As minutes stretched into an hour and the plane failed to reappear on any radar screens or make its scheduled arrival in Beijing, that worry escalated into a full-blown crisis. Where could a Boeing 777 simply vanish? The initial assumption, naturally, centered on the last known position, the point over the South China Sea where communications ceased. Thus began a massive multinational search operation initially focused intensely on these waters. Fleets of ships and aircraft from Malaysia, Vietnam, China, Singapore, the United States, and other nations converged on the area. Hopes were high for a swift discovery. Surely a crash in this relatively busy maritime region would leave an obvious debris field. Reports flooded in, oil slicks spotted from the air, floating objects sighted by ships. Each potential clue was pursued with urgency, dominating news cycles globally. But one by one, these leads evaporated. The oil slicks were from ships, the floating objects unrelated debris. Days turned into a week, and the South China Sea yielded nothing concrete. Frustration mounted, just as confusion reigned, and the search seemed to be hitting dead ends in both the South China Sea and the Strait of Malacca. A different kind of data emerged. Data that wasn't meant for tracking in real time, but held the key to the aircraft's ultimate fate. This information came from Inmarsat, a British satellite telecommunications company. Even though the plane's main communication systems, including the ACARS system, which sends routine engine performance data, had been shut down or stopped functioning around the same time the transponder went silent. A component of the satellite communication system on board MH370 continued to operate in a passive mode. This system automatically responded to hourly status requests or pings initiated by an Inmarsat ground station coordinating with one of its geostationary satellites positioned high above the Indian Ocean. Think of it like a phone periodically checking if it has a signal, even if no calls are being made. Crucially, the system logged these electronic handshakes. While these pings contained no explicit location, speed, or altitude information, engineers could analyze two key parameters from them: the burst timing offset, BTO, and the burst frequency offset, BFO. The BTO relates to the time it took for the signal to travel between the satellite and the aircraft, giving an indication of the distance between them. This allowed investigators to calculate rings of possible locations on the Earth's surface for each ping. The BFO relates to the Doppler effect, the change in frequency caused by the relative motion between the satellite and the aircraft. Because the satellite's position was fixed, the BFO provided clues about the aircraft's direction and speed relative to the satellite. By analyzing the sequence of these pings over several hours, Inmarsat and international investigation teams deduced something astonishing. MH370 hadn't crashed shortly after disappearing from radar. It had continued flying for approximately 6 more hours. The revelation that MH370 likely met its end in the vast, remote southern Indian Ocean presented an entirely new and unprecedented challenge. This wasn't the relatively shallow, well-trafficked South China Sea. This was an area thousands of kilometers southwest of Australia, known for its immense depths, rugged underwater terrain, and ferocious weather, the Roaring Forties. The defined search area along the 7th arc derived from that final satellite ping covered an initial expanse roughly the size of Mexico. Locating a submerged aircraft fuselage and its crucial black boxes in such an environment was akin to finding the proverbial needle, not just in a haystack, but in a constantly moving, abyssal haystack. Spearheaded by the Australian Transport Safety Bureau, ATSB, a multi-year, multi-million-dollar underwater search began, representing the largest and most expensive search operation in aviation history. It required deploying state-of-the-art technology. Initially, ships used sophisticated towed sonar systems, side-scan and multi-beam echo sounders to painstakingly map the seabed in high resolution, searching for anomalies that could represent wreckage. These devices were pulled slowly behind vessels, scanning wide swathes of the ocean floor, often thousands of meters below the surface. The sheer scale was immense. Imagine mowing a lawn the size of a small country, meter by painstaking meter. While the deep-sea search in the southern Indian Ocean drew a blank, clues began to emerge from an entirely different source: the ocean's surface currents. More than a year after the aircraft vanished, in July 2015, a piece of aircraft debris washed ashore on Réunion Island, a French territory east of Madagascar, thousands of kilometers away from the underwater search zone. This piece, quickly identified by aviation experts, was a flaperon, a control surface from the wing of a Boeing 777. Serial numbers and maintenance records confirmed the unthinkable. It belonged to MH370. This discovery was monumental. It was the first physical proof that the aircraft had indeed met its end, likely in a catastrophic event resulting in fragmentation. And crucially, that it had ended up somewhere in the vast Indian Ocean basin. The location where the flaperon was found, however, wasn't the crash site itself. It had drifted for potentially 16 months, carried by complex and powerful ocean currents across immense distances. Following the flaperon discovery, a scattered trail of other potential and confirmed debris pieces began to appear on coastlines across the western Indian Ocean. Beaches in Mozambique, South Africa, Mauritius, Madagascar, and Tanzania yielded fragments displaying characteristics consistent with a Boeing 777, some later confirmed as definitely or highly likely from MH370. These included parts of the engine cowling, cabin interior elements, and other wing fragments. The Barnacle Testimony. Among the pieces of debris recovered, the flaperon found on Réunion Island held more than just confirmation of the aircraft's fate. It carried silent witnesses clinging to its surface, barnacles, specifically goose barnacles of the species Lepus anatyphera. These small crustaceans attach themselves to floating objects in the ocean, and their presence on the flaperon immediately sparked scientific interest. Could these tiny hitchhikers tell a story about where the flaperon had drifted, and by extension, point towards the origin of its journey, the crash site? The answer, developed through painstaking research years later, appears to be a cautious yes, offering one of the most intriguing new lines of evidence. The key lies in the way barnacles grow their shells. Like tree rings, barnacle shells form in layers, incorporating chemical signatures from the surrounding seawater as they develop. Crucially, the uptake of certain elements and their isotopes into the shell carbonate is strongly influenced by water temperature. Scientists realized that by carefully analyzing the geochemistry of the different layers within the shells of the oldest barnacles found on the flaperon, they could potentially reconstruct a temperature profile of the waters the flaperon drifted through. Researchers, notably Associate Professor Gregory Herbert from the University of South Florida, and colleagues meticulously analyzed the oxygen isotope ratios, delta 18O, in the shell layers of Lepers barnacles. This ratio varies predictably with the temperature of the water in which the shell material formed. By sampling sequentially across the growth layers of the largest and therefore likely oldest barnacles attached to the flaperon, they could generate a timeline of approximate sea surface temperatures experienced by the flaperon during its long drift. The next step was to compare this reconstructed temperature record derived from the barnacles with extensive oceanographic data and models showing sea surface temperatures across the Indian Ocean during the potential drift period March 2014 to July 2015. If the flaperon started its journey further north along the possible flight path arc, it would have drifted through warmer waters initially. If it started further south, it would have encountered colder waters sooner. By matching the temperature sequence recorded in the barnacle shells to the temperature sequences predicted by drift models starting from various points along the seventh arc, the researchers could evaluate which starting points were most consistent with the barnacle's testimony. Listening to radio waves WSPR analysis. Parallel to the investigations focusing on physical debris and satellite data, another completely independent line of inquiry emerged. Utilizing a global network not designed for aviation tracking at all, the Weak Signal Propagation Reporter Network, or WSPR, often pronounced WHISPER. WSPR is a protocol used by amateur radio operators worldwide to test radio propagation conditions. Operators transmit very low-power signals, and a global network of receiving stations automatically logs when and where these faint signals are detected. It essentially maps how radio waves travel through the atmosphere at any given time. Aerospace engineer Richard Godfrey proposed a novel application of this vast WSPR dataset.
There's no reason why we shouldn't be preparing a new search and planning for that. It will only take one more search and we will find it.
His theory was that a large aircraft like a Boeing 777 flying through the paths of these weak radio signals could cause detectable disturbances or anomalies in their reception at the ground stations. An aircraft fuselage and its turbulent wake could momentarily reflect, refract, or attenuate these signals in predictable ways. If MH370 flew through numerous WSPR signal paths during its final hours, could the historical WSPR database reveal its track? Godfrey undertook the mammoth task of analyzing millions of WSPR data points recorded on the night of March 7th to 8th, 2014. He looked for instances where a signal between a known transmitter and receiver experienced an unusual fluctuation or temporary interruption that coincided precisely with the predicted times and locations MH370 might have been flying based on the Inmarsat data. He hypothesized that each anomalous detection represented the aircraft crossing a specific radio signal link. Zeroing in the new proposed search zone, the culmination of these diverse and innovative analyses, the refined interpretation of the final Inmarsat signals, the geographical constraints suggested by the barnacle geochemistry, the potential flight path traced by WSPR data disturbances, and updated oceanographic drift modeling based on all recovered debris, has led independent researchers and groups like Ocean Infinity, a private seabed exploration company that conducted its own search in 2018, to propose a new, more tightly defined search area for MH370. This proposed zone isn't entirely divorced from previous efforts. It lies adjacent to, or partially overlapping, the original 120,000 square kilometer area searched by the ATSB, but crucially, it incorporates the insights gained since that search was suspended. The barnacle analysis, for instance, provided strong evidence favoring a specific latitudinal band along the seventh arc, suggesting the crash might have occurred slightly outside the area most intensively scanned previously. perhaps further south or in regions with particularly challenging terrain that might have hindered detection by earlier sonar methods. Richard Godfrey's WSPR analysis tracing a potential flight path intersects the 7th arc at a specific point around 33 degrees south latitude. This location aligns remarkably well with the latitudinal range suggested by the barnacle temperature studies and also fits within the broader calculations from debris drift modeling. When combined with refined analysis of the very last satellite communications, particularly the implications of the final partial ping potentially indicating a rapid descent or impact, these converging lines of evidence point strongly towards a specific, manageable target zone. Unanswered questions. Even if a renewed search guided by these scientific breakthroughs successfully locates the wreckage of MH370 deep beneath the waves of the southern Indian Ocean, a profound and painful question will likely remain: why? Finding the aircraft's final resting place confirms the where, but it doesn't automatically unlock the why behind its deviation and disappearance. The physical evidence of the wreckage itself, particularly the cockpit voice recorder CVR and flight data recorder FDR, the crucial black boxes, holds the best hope for definitive answers, but their recovery and the condition of the data they contain are far from guaranteed after years submerged in the crushing depths. In the absence of concrete evidence from the aircraft itself, speculation about the cause has run rampant for over a decade. The main theories broadly fall into a few categories. Was it deliberate pilot action, an unthinkable act of mass murder-suicide by one of the experienced pilots? This theory gained traction due to the seemingly deliberate disabling of communication systems and the precise navigational nature of the flight path deviation. Or was it an unlawful interference like a hijacking perhaps by passengers or stowaways that went tragically wrong?